Hello everyone, I'm Tim Pearce. I'm going to talk about work I published earlier this year with Sasha Krivov and Mark Booth, where we proposed and investigated a new theoretical model to potentially explain the mysterious hot exozodis that are detected around many main sequence stars. So first of all, what do we mean when we talk about hot exozodis? Well, observations show that about a fifth of main sequence stars exhibit excess near-infrared emission. These stars cover a broad range of main sequence ages and a broad range of spectral types. Now, various groups have modelled this emission and they find it's consistent with populations of very hot dust of order 1000 Kelvin located very close to the star. These models also infer that the dust is composed of very small grains, potentially submicron in size. But the nature of this dust is hard to understand. Such hot dust should rapidly sublimate, and such small dust should rapidly blow away. So this problem has led to the hypothesis that some mechanism exists to either trap dust and keep it close to the star, or to continually supply new dust to the region. Now, a wide range of potential mechanisms have been investigated, but so far none have fully explained both the phenomenon and its ubiquity around such a broad range of main sequence star types and ages. So to demonstrate the problem, I want to show what happens to a dust grain released close to a star. So here we have a plot which has on its horizontal axis the radial distance from the star, and on the vertical axis the grain size. And the dot in the top right of the plot is the dust grain that we're about to release. Now I'm going to show what happens dynamically to this particular grain as an example, but the general behaviour of a dust grain in this region is qualitatively similar over a very broad range of initial parameters and dust compositions. So what happens to this grain? Well, first of all, the grain spirals in towards the star under PR drag, and I've shown that here. The grain slowly spirals in and gets closer and closer to the star, and as it does so, it gets hotter and hotter. Now it keeps spiraling in until it gets so hot that it starts to sublimate. And it does this extremely rapidly, and this is stage 2 on the plot. At this point, the grain is essentially boiling. It's rapidly turning into gas. And so it very quickly shrinks by orders of magnitude in size. As it shrinks, its beta value increases, so radiation pressure becomes more and more important. Finally, as the grain shrinks, radiation pressure eventually pushes it onto ever more eccentric orbits, until eventually the grain becomes unbound and blows out of the system. Now the important thing to note is that this simple model cannot explain the observed near-infrared excesses, and the reason is that this dust produces far too much mid-infrared emission compared to near-infrared emission. This is because the grains spend the vast majority of their time in stage 1 spiraling inwards towards the star. Grains that are spiraling in are comparatively cool and comparatively large, which means they're really good at emitting in the mid-infrared. To emit efficiently in the near-infrared, grains must be small and they must be hot, which means we need them in the bottom left of this plot in stages 2 and 3. But as we've already said, the grains go through stages 2 and 3 extremely rapidly. So this means that dust in this model produces far too little near-infrared emission and far too much mid-infrared emission to be compatible with observations. So this model doesn't work, but the question we ask is what happens to the gas that's released by this sublimation process? What dynamical effect does it have on the dust grains in this picture? The scenario we investigate is described in Pearce, Krivov and Booth 2020, and we give a quick overview of the scenario now. So first we have the star, and exterior to the star we have a source of dust, which can either be a debris disk or it can be comets. It doesn't matter what the source of dust is, provided that it releases dust exterior to the sublimation region of the star. Now as dust migrates inwards under PR drag, and when it gets close to the star it sublimates, releasing gas. So this is exactly the same picture as we showed on previous slides. However, here's the new bit. So now we've got gas that's close to the star, and we know that gas can affect the dynamics of dust grains. So in our gas trap model, grains get caught in this gas and held close to the star, and it's these grains that are the source of the observed near-infrared emission. And then finally, we don't expect these trapped grains to survive forever, but rather they'd undergo various destructive processes such as collisions. So finally, we expect there to be another population of dust in this model, which is basically sub-blowout ejecta that's been released by the grains trapped in the gas that's escaping from the system. So let's have a look now at how gas can affect the dynamics of dust. So to allow a comparison, first of all, I again show dust evolution in the absence of gas. So on the left, we've got a similar plot to the before where I show grain size versus distance from the star. And the grain demonstrates this sort of typical three-stage evolution that we already talked about. And on the right, I've just shown those same two quantities, so grain size and distance, but this time versus time, just so you can get an idea of the different timescales involved. But the important thing to note is that the grain spends a very long time migrating inwards under PR drag, and then when it gets close to the star, it very rapidly shrinks and gets blown out of the system. Right, so that's the evolution in the absence of gas. Now what happens if we include gas? Now, on the left plot, I've now overplotted the gas density profile that we assume in our model. Now, this is just a simple analytical model of a viscously spreading gas disk, which has new gas being continually added to it at the sublimation radius. So basically this model assumes that grains are sublimating at the sublimation radius and that the gas that's released is then spreading out into a disk. And it's important to point out that the gas density that we use in this model is extremely small. So in this particular example, it's only about 10 to the minus 17 grams per cubic centimeter at the sublimation radius. Right, so now we've got our gas. So now let's rerun the simulation and see what happens to the dust grain. So these red lines show the grain evolution in the presence of gas. Now we can see that the grain first of all migrates inwards, and when it gets close to the star, it sublimates, exactly as before. However, as the grain shrinks, the two behaviours now diverge. As the grain gets smaller and smaller, it begins to notice the gas. And what the gas does is that it drags the grain pericentre out away from the star, and this protects the grain from further sublimation. The gas also circularizes the grain orbit, so we don't get eccentricity increase and the eventual blowout that we did in the gas-free case. And then finally, the gas is trying to pull the grain outwards. Meanwhile, PR drag is trying to pull the grain inwards. And so eventually what happens is the grain moves out to the point at which the force from PR drag balances the force from gas drag. At this point, the grain migration stalls and the grain is now trapped. So what we've done in this model is we've managed to trap a submicron grain close to the sublimation radius, which is exactly what we wanted to do in order to try and explain the observed near-infrared emission. So that was an example of what happens to one particular dust grain. The next thing to look at is what are the general parameters of the dust populations that get trapped according to our model. Here we have a plot that's similar to before, showing grain size versus distance. On the top plot, I've shown a sunlight star, and on the bottom plot, a more luminous A-type star. Now these dark grey regions show the sizes and locations of dust grains that it's possible to trap according to our model. The first thing to note is that it's possible to trap a range of dust grain sizes, and secondly, that the location of trapped grains scales with the luminosity of the star. The third thing to point out are the dashed horizontal lines, which show the blowout size. Grains below these lines are so small that they're rapidly blown out of the system by radiation pressure. And the key thing to note is that the gas trap model cannot trap grains that are smaller than the blowout size, and I'll come back to this point in a minute. So these are the grains that we can trap in gas. Now let's have a look at the properties of real grains as inferred from observations. So starting with the G star, this light grey region shows the properties of grains required to reproduce observations. A population of grains with a size and location corresponding to any point within this shaded region will reproduce the observed near-infrared excesses. And we can see that the grains that we predict to trap nicely overlap with this region. This means that the gas trap model can reproduce observations of near-infrared excesses around sun-like stars. So that's great. Now let's see if the model can also reproduce observations around A-type stars. And the unfortunate answer is no, it cannot. The trapped grains are in the right place, but they're about an order of magnitude too large. And this comes back to the problem that we cannot trap grains that are larger than the blowout size. Now we go into a lot of detail about this in the paper. We tried various solutions. For example, we model the emission from ejecta that's released from collisions between trapped grains. But despite this, the fact remains. It is very difficult to get small grains to remain close to A stars for long enough to reproduce near-infrared excesses. So given the successes and failures of the gas trap model, it's worth looking at what observational constraints the model can and cannot satisfy. So here I've listed the main constraints on hot dust as inferred from observations, and I just want to quickly go through these. So first of all, the dust location scales with star luminosity, and we've shown that this is a natural outcome of the gas trapping model. Likewise, dust location and grain size around sunlight stars is also reproduced. We've shown that the dust location around A-type stars is reproduced by our model, but that the grain size is about an order of magnitude too large. Now, because we trap small grains and any large grains sublimate down in size, we are able to produce a very steep size distribution. We've also shown in the paper that we can trap grains for long enough that we can produce significant near-infrared emission without much mid or far infrared emission. And finally, whilst gas is not detected around all stars with near-infrared excesses, we show in the paper that the quantity of gas required is so small that we do not necessarily expect to detect it with current instrumentation. So we can see that whilst the gas trap model is not perfect, it does reproduce a wide range of observational constraints. But unfortunately, near-infrared excesses around main sequence stars remain a mystery. Okay, that's all the time I have, so I'm just going to leave you with my conclusions. If anyone is interested, please have a read of our paper where we go into a lot more detail. In particular, we also discuss general problems that any hot dust explanation for near-infrared excesses will face. Okay, that's all I have to say. Thank you very much for watching.